Thanks for the intro and thank you for having me. It's really nice to be back around there, folks. Today's talk, as you can see from the multitude of logos on the screen, is going to be a collection of different projects that I've worked on at various different points in my career so far. But they all center on the same system, which is the El Niño-Southern Oscillation system. This is a little bit redundant, as Monica did this for us already. But I would like to pay my respects to the elders, past, present, and emerging of the Gadigal people of the Aurora Nation. So what I'm going to do today is first give you a little overview of the system under study, the El Niño-Southern Oscillation phenomenon. And then touch upon three different projects, thank you, which are all very different mathematical framings of the same system. So the first one is going to use ideas from dynamical systems theory, or chaotic systems, if you've heard of that. The second will be a bit more familiar to folks in this room because it's based on Bayesian quantile regression. And the third will be based on a simple discretization of the system into categories. And then I'll give you a bit of a wrap up. So El Niño-Southern Oscillation is what ENSO stands for, and we're just going to call that ENSO. You've probably heard of El Niño and La Niña events in the news. They happen every few years. An El Niño is a warm event and a La Niña is a cool event. And these arise in the eastern and central tropical Pacific. So in that picture up there, you can see North America on the globe, and this is the equatorial Pacific. During an El Niño, you get warm temperature anomalies at the surface of the ocean. And during a La Niña, you get cool anomalies, and you get changes in the wind field as well. Here at the bottom is a graph of an index that we use to measure ENSO activity, showing its progression over the years. And you can see they happen sort of every few years where you get a really large spike in red or downward spike in blue. Now, the reason why we care about this oscillation is that they have very widespread impacts. Almost every continent, actually every continent is affected in some way or another by the changes induced by these events. And the way they induce these changes is because they're changing the surface of the surface temperature of the ocean, they affect the amount of evaporation and the wind field above it. And that then induces a perturbation to the atmosphere that can propagate. And those propagating waves perturb weather all around the globe. For Australia in particular, El Niño typically means drier conditions and hotter conditions. And La Niña typically means wetter conditions and cooler conditions. So to delve a little bit into what the physics of the system looks like, we need to first think about what the tropical Pacific Ocean looks like under normal circumstances when there's no El Niño or no La Niña event. So here, this is a somewhat distorted map. Here, this is North America and South America on your right. On your left is Australia. And the warm colors indicate the sea surface temperatures, which are warmer in the western part of the Pacific. Because of that warm water, evaporation occurs that induces convection, and you get quite tall clouds that are associated with thunderstorm activity and rising air. At the opposite end of the Pacific, you have cooler waters. And the reason for that is because you have winds blowing from the eastern side to the western side, which means they're pushing water at the surface away from the coastline and away from the equator in a way that leads to colder water that hasn't been exposed to the sun rushing up to the surface. So you get this temperature gradient across the Pacific Basin. And so above the high temperatures, you get low pressure, and so you strengthen those winds going across. So all of these components are in a nice balance with each other. And El Niño and La Niña events are basically when that balance is tilted in one direction or another. So in an El Niño event, you get warmer waters across the whole Pacific, and that weakens the winds. It changes where the convection sits, and that results in those waves that go perturb the weather in other parts of the world. In a La Niña event, you end up with the cooler water becoming more widespread because the upwelling got stronger, and you push that convection out as far west as it can get, and you change the convection the circulation over the tropical Pacific. Now you'll notice there's also a thermocline marked here in this three-dimensional diagram, and that is the interface between the warm waters that are warmed by the sun just through exposure and mixing, and the cool waters that almost never see the sun. So there's quite a sharp interface, and you know that warm fluids are lighter than cool fluids, and so they behave a bit differently. They have different densities, and this sharp interface gets pulled about by the upwelling induced by the winds. So when you have stronger upwelling, you get this slant in the thermocline, and when you have less upwelling in an El Nino, you get a flattened out thermocline. Now, the way in which this proceeds, how you go from the normal state to one of these events, is through something called the Bjerknes feedback. So let's say you induce some sort of perturbation. Here you could have warm sea surface temperatures in the East Pacific. Let's say there's a longer period of sunny days than usual, or maybe a storm passes through or changes the circulation. And so now you have warmer SSDs. That weakens that gradient across the Pacific basin between warm and cold. And that weakens the winds that push the water away from the coast and the equator. That means that the upwelling of cold water is reduced. And that means there's nothing to counteract that warm anomaly that was in the east. So you end up with a setup where you're reinforcing that warm anomaly. So that leads to an El Nino event that can last for several months of the year. And in the opposite direction, if you get colder SSDs in the East Pacific, the same chain of events can happen in the opposite direction, and you get a La Nina event. So the fact that there are these feedbacks in the system allows small perturbations to grow, and that makes this system very challenging to study and very challenging to predict. Now, just to give you a sense of how challenging, this is an example of a forecast of El Nino from one of our climate models that's actually used in practice. You can see that this ensemble is all started at the same point. And this is a physical model using the laws of physics. And the only difference between the different ensemble members is there's a very small perturbation of maybe 0.001 degrees C scattered across the basin in each one. And over time, so this is the number of months since you start, you see they rapidly diverge, and the prediction becomes effectively meaningless about 2 years out. And this is because any very small perturbation can be quickly amplified through those feedbacks that I was describing. So this puts it in a class of systems known as chaotic systems. And the first of the 3 projects I'm going to showcase is using attractor reconstruction, which relies on the mathematics of chaotic systems. So in a chaotic system, a typical way of characterizing it is to plot the attractor, which is a manifold that characterizes all the possible states of the system. This is the classic Lorentz attractor. It's a paper from 1967, which is every dynamicist's favorite paper. So you get 3 variables, and they you're just plotting the different points in time of those equations, and you get these 2 lobes. So there are these 2 different regimes of behavior that emerge. And that's quite common in chaotic systems. Now, this shows all the possible ways that the trajectory can evolve. If you look at a point right here up in the top right corner, you can see that similar states are leading to a similar future. If you are up at the top here, then you're going to end up in the bottom here. Like that's quite clear that that's the direction in which the trajectories go. If you're in the middle of the attractor, however, a very small perturbation can push you into this lobe or into the other lobe. And that's where that sensitivity to perturbations comes from. When you're in a particular kind of state in the system, you're more sensitive to these perturbations. So the lack of predictability doesn't come from us not understanding the physics or not having high enough resolution. It's just a mathematical property of the system. So now you can take a data-driven approach to this, and we use a method proposed by Sujihara et al. In 2012. You can, instead of finding the X, Y, and Z of that particular system you're trying to study, if you don't really know the underlying equations, you can pick a single axis, a single variable, just any index of your choice, and find lags, tau, where if you plot this with 0 lag and then a lag of tau and a lag of 2 tau on the 3 axes, you will end up with a shape that preserves the properties of the original attractor. So this is called a shadow manifold, and it preserves that property of having essentially 2 possible lobes of behavior and one region where your behavior might go either way. So we did this for the tropical Pacific system. We used the Niño-3 index, which is just an average of sea surface temperatures in that region shown there. And that's a very commonly used measure of El Niño and La Niña activity. We then do this lagging procedure and make that structure for 1 to n number of dimensions. We tested up to 9, and and you do these lags for each one. So in each system, you can then test if if my neighbors near me at the next time step are near me still, then I have made a good prediction. So it's called a simplex, where you average over your nearest neighbors, and you consider that the prediction of the next time step. You test how good that prediction is at each point in the structure you've created. Ultimately, you select a pair of n, that is the number of dimensions, and tau, that's the monthly lag. That gives you the best predictions, and that should correspond to the shadow manifold. To do this, we use something called the Zebyak-Kane model. So this is a very data-intensive way. You can only really get certainty in this method if you have a very large amount of data, but we've only observed about 40 years worth of sea surface temperatures using satellites. So to get around that, we used a physical model, which is designed to simulate that system that I just described. And I put all these equations there just for you to get a sense of how it's set up. The colored entities are time varying, spatially varying fields. So there's velocity in the ocean and the atmosphere and in different directions, and the temperature of the ocean surface and the height of the ocean surface. This is an old model that was actually produced in 1987. So well before many people in this room were born. Because it was produced so long ago, on modern computers, it runs in an instant. It is super fast. So I was able to run it to give me a simulation of 150,000 years worth of data in about 4 hours. Like I just had to leave it overnight. So this gave us a massive amount of data to work with. And from that data set, I was able to construct the shadow manifold. So this is what it looks like when it traces out that shadow manifold. We found it was three-dimensional with a lag of 6 months. So you can see here there's lag 0, lag 6, and lag 12 as the three axes. And what we found was that the system, as it traces this trajectory, draws these large loops, and then it goes into this smaller set of orbits before jumping to these larger orbits again. So it's displaying these two different regimes of behavior where you have small loops and large loops. So here you can sort of see that statically a bit more clearly. Now the radius of an orbit here, so it might be easier to think of it in terms of the mean first, actually. If you think of what the mean of all these points is, it's essentially the centroid of that geometric figure. And if you think of what the standard deviation is, it's the distance from the center. So you're getting a low standard deviation orbit when you're not far from the center, and a high standard deviation orbit when you're far from the center. And if you look at just the distribution of 15-year standard deviations and means, you can see that those standard deviations are nicely bimodal. So you really capture those two regimes in the standard deviation. You don't capture it so much in the mean. And this actually matches up with something we've observed in reality. We've seen periods of low and high ENSO activity that last for a few decades, and they do switch between these two types of behavior. Now, something you can do once you have the shadow manifold, which represents the attractor, is figure out which parts of the attractor are those predictable parts and which ones are the unpredictable ones. So the parts that I've colored in, those little cubes, were the most predictable parts of the attractor. So if you're in the middle of that blue bit there, the system is about to spend the next 15 years or so in the low variance orbit. If you're in one of the yellow ones, it's going to spend the next 15 years or so in the high variance orbit. So once you've detected these on the shadow manifold, you actually also know what points in time those were. So you can go to your physical model and extract what was happening in the ocean and atmosphere during that time. So the column to focus on here is the second one, which shows the mean. So I'm showing the mean state of the physical model within those blue states. So the very predictable states are the ones where you have this particular pattern of sea surface temperature anomalies, this particular pattern of thermocline tilt, and this particular pattern of the winds. So to summarize what we found there, we were able to take a climate model and reconstruct its shadow manifold. That allowed us to see that there were two different regimes of behavior of the system. And in the system, we were able to locate the particular states from which we could make reliable predictions of which of those two regimes it was going to spend time in. So we wrote a paper on this a while ago, if you want to look that up. And with that, I'll move to project 2, which has to do with Bayesian quantile regression. Now, the version of El Niño and La Niña we just looked at was temporally invariant in that there was no background change, there was no climate change happening, there was no warming. And if you're interested in understanding the patterns of warming, you need to think about it differently from a mathematical standpoint. So one way that we have come up with was to apply Bayesian quantile regression. Now, global climate models, these are, again, physical models of the nature that I described before, but for the full globe instead of just the Pacific. People have run these with simulated climate change, so simulated extra greenhouse gas forcing, so that we can see how the atmosphere and ocean respond to that. And that's how we have projections of how fast the Earth is going to warm under climate change. Now, when we look in these models at how El Nino events behave, they predict that there will be an increase in extreme El Nino events. So in the historical period, I'm sorry, the text is a little faint for those in the room. This graph says that you get one extreme El Nino event per about 27.6 years. But in the future projections from those same models, when you have active climate change, you get one extreme event per about 15 years. So you get a much higher frequency of extreme El Nino events. People have also looked at the distribution of temperatures in that Niño 3 box that we were using as an index before, and they've seen that there's a general shift towards warmer temperatures. So the control period is here in blue, and the red is the climate change period. You can see most of these bars are to the right. However, at the same time, this comes with one massive caveat, which is that these climate models often don't quite simulate the tropical Pacific system correctly. So this was a paper in 2019 that showed this point very clearly, where these boxes indicate the observed values. So the orange diamonds are the easiest to see, so focus on that. This is the observed behavior, and the filled blue and black diamonds are climate models. What we're seeing on the x-axis is the trend in that Niño 3 value. On the y-axis, we're seeing the end year. So they did this for 30-year periods ending in 2008, 2009, 2010, and so on. And what you see is a clear divergence of behaviors. So in the real world, as climate change has progressed, we've seen the Niño 3-4 remain sort of at a pretty steady trend. Whereas in the climate models, they're warming really rapidly in that region. Now, this has consequences for how well they're actually able to simulate El Nino and La Niña events. So we need to take that previous result on the last slide about extreme events becoming more frequent with a massive grain of salt. And we don't really understand what this means for predictions of more extreme El Niños. In terms of the feedback that I was telling you about earlier, what we're doing is what we're seeing rather is that the SST gradient across the basin is getting weaker in the climate models in the future, but it has been getting stronger historically. And this means we could set off behaviors that are quite opposite. However, this doesn't quite tell us about the frequency of these events, and that relationship is not very well understood. As we saw before, the mean and the standard deviation on decadal timescales in this system can look quite different. And the standard deviation is essentially a proxy for how active El Nino and La Niña events are. If you get more of these events, your standard deviation goes up. So if you look at the graph of El Nino and La Niña events, you might be able to see that El Nino tends to go up to higher peaks, and La Niña is a bit more muted, but lasts for longer. This asymmetry means that having more El Niños does two things. It increases your standard deviation, but it also increases your mean. So those two things are not independent. And they can be quite biased by what is happening at essentially the top end of your distribution. So to try to understand this, rather than looking at things that are symmetric, like the mean and the standard deviation, we decided to use quantile regression, where we can look at the individual quantiles and how they are changing. So we use a spatio-temporal technique that was put forward by Brian Reich. What we're essentially going to do is estimate the different quantiles of the distribution rather than just things like the mean and standard deviation. So this regression will give us the different lines fitted in this way. But we are also setting this up with a GP prior on the spatial information so that we preserve the smoothness of the fields. In terms of how this is actually set up, this is what it looks like. There is the quantile function, which tau is the quantile level that you're looking at. So maybe you're looking at the 5th percentile or the 20th percentile and so on. S is the spatial point or location. T is the point in time. We're doing this as a simple linear regression. So you've got an intercept Q0 and a trend term Q1. These intercept and trend functions are constructed as a linear combination of basis functions. So the basis functions, I'm not going to go into a lot of detail in how they're designed, but essentially they are in these shapes so that they would give you quantile functions that are smooth, as in the picture on the right. The quantiles are set up as this formula. And what we are going to need to estimate using MCMC is beta, which is a function of space, and theta, which is also a function of space. So that was set up using a Gibbs sampler. Now, in the code that was provided by the author of that original paper, that was set up for a relatively small data set that converged quite quickly. And when we actually tried it on our tropical Pacific temperature data, it wasn't quite up to scratch, which is where our lovely Travis came in and saved the day, where he got to the bottom of why it wasn't working and put in some really important improvements. There's more to it than this, but a very quick overview of those improvements. We found that there was an asymmetry in the way that probabilities were being calculated. And that meant that if you did it for enough iterations, the errors accumulated in a strange way and you got probabilities that were greater than 1 or less than 0. And so we had a replacement for that. It ran for really long. And we needed to be able to run this for multiple data sets in multiple different ways and test out different things. So in order to do that, Travis parallelized the code, set up a bin packing algorithm, which distributes the loads efficiently between the different nodes that it's been parallelized on, and made custom definitions of a few standard packages so that they would run faster. Overall, this brought the runtime down significantly, and this bin packing algorithm in particular halved the runtime that it took. So with Travis's help, we started being able to look at some results. So in this case, we are tracking the convergence of the iterates of beta. Of course, we do this for theta as well. Here you're looking at the spatial field, and here you're looking at the sample number. I'm sorry, I might have missed a slide. There's supposed to be another image here which isn't showing up. I apologize. So just to orient you, this is where South America is, and this is where Australia is. So the x-axis basically spans the Pacific Ocean as you would see it on a map. So left equals Australia, right equals South America. And as you go up along the y-axis, that tracks the iterations as you go along the MCMC chain. We found that there's a lot of variation in how quickly things converge based on where you are spatially. And we had to run this well beyond 15,000 iterates to actually start seeing convergence. So you can see in particular where these colors get darker, this is converging quite slowly. You can see there's quite a bit of evolution over time, where you see a sudden increase and then up the plot, you see basically a stable value that looks like this at the bottom. And so you got quite quick convergence. So we devised ways to keep track of this across the full spatial field. Here we're looking at the maximum change across the full spatial field between one iteration and the next. And you get, you can see that those really big spikes start to go down over time. Now, the results that we got for this are here for one single data set. We are trying this over multiple data sets, but I'm going to just focus on one for now. This was the figure that I intended to have on the previous thing, so you can see where you are on the map. So we saw that there's significant variation across the spatial domain, as well as variation across the quantiles of the distribution. So the y-axis is showing you the quantile level now. On the far left of the picture, or the west, there's a region of warming where the warming can be quite uniform across the quantiles. It's warming a lot more rapidly than the rest of the ocean, which is consistent with what we observe. In the Central Pacific, we found that the warming was quite slow, or even that there were a few places where there was a bit of cooling. And at the right of the picture, in the East Pacific, we found there was significant variation across the quantiles. And this makes sense because this is the part of the ocean where you expect the most El Nino activity. So you can see right here at the top, this is sort of in shades of light green and yellow. And if you look right at the bottom near the lower quantiles, you get shades of dark blue. And what that implies is that the distribution is actually diverging over time, because the lower quantiles are sort of staying stable or decreasing. The higher quantiles are increasing. And the higher quantiles are increasing at a rate quite a bit faster than the median. What this tells us is that El Nino events themselves are becoming more extreme, in this data set at least. But the mean and the background state are not evolving quite as fast. They're not responding to climate change at the same rate that the events are responding. And that in itself is quite a new result in this field, where we've not previously been able to do that kind of separation before. So to summarize, this gives us a more nuanced picture of the changes under climate change in the tropical Pacific than what we've been able to get so far. We have a distinct area of rapid warming in the West Pacific and a diverging distribution in the East Pacific. And this has implications for the difference between how the average background state is responding versus how specific El Nino events are responding. We're also in the process of validating this and comparing it with other data sets. So watch this space. All right, moving to part 3. This is a project that I'm working on at CSIRO with a few collaborators there. It arose essentially because we spent a lot of time looking at this graph. What you've got on the x-axis is the Niño-3 index. By now you know what this is. What you've got on the y-axis is the spring rainfall averaged over Eastern Australia, which is, that's the season and the part of Australia that's most affected by El Nino and La Niña events. So when you look at the scatter plot, it's quite clear that if you look at just the El Nino years, there is not a linear relationship between how big the El Nino is and how much the rainfall in Australia is affected. That is not at all a clear relationship. And similarly, if you were to look at La Niña, there's a little bit more of a relationship, but it's mainly because of this extreme outlier. Again, this is not a very clear predictor, which implies that just knowing whether you're going to have an El Nino or not is useful without necessarily knowing, is it going to be a big El Nino? And similarly for La Niña. However, the way that we currently do ENSO forecasting doesn't have that focus, and instead uses measures of error like the root mean squared error, which would give you a very large estimate of error, even if you do predict an El Nino correctly, but you have a slight shift in the timing, or if you have some inaccuracy in the magnitude. So both these graphs are showing things that are essentially correct predictions that yes, there will be an El Nino, but you get a measure of error that doesn't tell you that you're getting a good result. So what we are going to do is just to look at the category itself and take a probabilistic approach to this. Is this category probable or not? There are pros and cons to doing this. We're essentially lowering the bar for what we want our model to be able to forecast. So this means that that's reduced detail. So if you're interested in the exact spatial pattern of El Nino, you might lose that. And it doesn't really leverage all the possible sources of information. However, there are some advantages. And that is that by lowering the bar, you could increase the level of confidence you have in the forecast that you communicate to stakeholders. It's consistent with the way that agencies around the world really talk about El Nino and La Niña events. They announce now it is an El Nino, or now the El Nino has ended, rather than saying, rather than going into all the details of the trajectory. So it is consistent with the way it's communicated to the public. And the third reason is that people in machine learning have spent very long thinking about categories, how to classify things into categories, and whether you have correctly classified things into those categories, which means they have a number of statistical tools to evaluate categorical forecasts very well. So we don't really have to come up with our own. There's a whole field of this out there. So what we're going to do is start by looking at the historical pattern of categories. And then from there, we'll look at skill in a suite of climate models from around the world. So to do that transformation from a continuous thing to this discrete categorical forecast, we're just going to take the distribution and divide it into three. So we've got terciles. The uppermost tercile is an El Nino event, lowermost tercile is a La Niña, and the middle is a neutral year. We also know that on average, El Nino and La Niña events last about 6 to 12 months. And this means that you're only going to get one of them per year. You're only making about one forecast per year. So you don't need that full trajectory. We also know that these typically peak in December and January. So we also don't have to care about the timing. So we just need this one bit of information every year, where it's one of three things: La Niña, neutral, El Nino. So I took a large hindcast, which is, it's a type of data set in climate science where you initialize a forecast in each year. So it starts in 1960. You initialize a forecast in 1960 and run it out for several years, see what the model predicts. Then you take 1961, observed conditions of the world go in at that year, make a prediction from there, 1962, and so on. So you have this series of predictions, and so you can test how skilled your model is over many, many years that way. So starting with the historical pattern of this, this is a transition matrix of those three states, where the transitions are from one year to the next. So you can go from La Niña, neutral, or El Nino in the first year to La Niña, neutral, or El Nino in the second year. Now, as you know, I'm going to assume you're all very familiar with graphs and transition matrices. As you know, there should be 9 possible transitions. And since we set it up such that these are terciles, they're all the baseline probability would be equal between the 3 possible categories, right? The color here is showing you historically which of these are most probable. So now if you look at the El Niño to La Niña transition, that's very probable. If you look at the neutral to La Niña transition, that's very unlikely. So that's how you interpret this picture. Now, how important is this? How significant is this historical pattern? We ran a bootstrapped chi-square test, which is, it essentially does the same as a t-test in continuous space. It's just the discretized version. And what we found is if you start in a La Niña, your random chance probability is 1/3, 1/3, 1/3. So you're tossing a three-sided coin. And we found that they're not significantly different from that random chance. If you look at a neutral event and what happens from there, we found that this is significantly different from the 1/3 uniform probabilities across possible states. For El Niño, that only works if you lower your confidence threshold a little bit. So I'm going to call that quite borderline. Now I took those hindcasts and ran that on 9 different climate models. So I did the same calculation of the probabilities on 9 different climate models that were basically running in their free state, where no perturbation is being added. I don't expect you to sit and interpret all 9 of these pictures. These are the sort of headline results from that. 9 out of 9 models actually had this feature that neutral years are most likely to be followed by El Niño. Most models agreed on what happens after neutral years. What happens after El Niños, there was a majority, but a smaller majority agreeing. So some of these characteristics actually are being captured correctly by climate models. However, if you take this and do the same thing when a model is initialized, that is, I give the model all the information about this year's current physical state, and then I run it for the next year, rather than just seeing what happens while the model runs freely, that consensus changes quite a lot. So you end up performing quite a bit worse after neutral years when you actually put in all that information from observations and run it from there. So there's something about that perturbation procedure, which I mean, it could be the way that, the way that we as a society, not me, I didn't do this personally, but like, the way that that we are putting in the information, maybe we're doing it wrong. But it could also just be that we are in a sensitive state, like what we saw. And so adding even a small perturbation or a small inaccuracy is enough to set it off veering in some other direction where it's not supposed to go. So thinking about that sensitive initial state, we found that when you look at a neutral state, the skill is actually very bad across models. So you've got some models that even gave us negative values. So they performed worse than chance. Whereas if you look at La Niña, the models were able to take in that information and perform quite well. So this is consistent with what we found in the first project, where you have some states that are very sensitive to perturbations and some states that are not. So it seems that La Niña is not sensitive to perturbations, and you can actually predict quite well what's going to happen next. Neutral is very sensitive to perturbations, and you're better off just not trusting the model. El Niño is somewhere in between those two. Another thing we can do with these categories is assess how trustworthy different models are. So this is, I'm just giving you an example of one finite model. But the situation in which we find ourselves whenever we look at a forecast from, the Bureau of Meteorology or whichever agency, is they've made a forecast. Now, how likely is that forecast to come true? So that's what we're going to assess. And setting it up in this categorical way means that it's very easy to frame that question as a conditional probability, right? So given that my model has predicted that it's going to go from El Nino to La Nina this year, it seems quite likely to be correct. But if it happens to be a neutral year right now and the model predicts it's going to be a La Nina, it's doing quite poorly. So here, the best performing transition is when you go from La Nina to El Nino. Models seem to do that really well. Whereas when you go from neutral to La Nina, the models predict that, but then it doesn't end up coming true. It actually comes true only about 20% of the time. The way we assess skill right now doesn't account for these changes at all. We're getting a range of something like 20% to 80% in our skill, but we don't account for that in how we communicate forecasts or how we speak about the uncertainty around forecasts. So yeah, you get a typical range within any model of 20 to 70%, and different models have different preferential skills. So the model that the Bureau of Meteorology is running is going to give you a slightly different skill than the model that the UK Met Office is using, which is a bit different from the Japanese agency and so on. However, one thing they all seem to agree on is that going from neutral to La Nina is something they predict and doesn't end up coming true very much. So there's some sort of bias in the way these models work that's giving you La Ninas when it's not supposed to from a neutral state. You can also look at, instead of using 3 categories for your forecast, just 2 categories where you say, will it be a La Nina or not a La Nina? Will it be neutral or not neutral? And that actually becomes something that has pretty significant skill in some situations. And again, this is something that we're not looking at currently, but would be very useful for a stakeholder that cares about whether it's going to be a rainy year or a wet or a dry year. So this is just a wrap up of that. And what we want to do next is try looking at whether this varies depending on the season in which you start your forecast and examine sort of longer sequences of events. I'm actually going to the Bureau of Meteorology next week to have meetings with them about how we can use this kind of system to produce uncertainty bounding around the forecasts that they issue, or rather maybe even statements around confidence of a forecast. So to summarize, we have looked at 3 different ways of looking at the ENSO tropical Pacific system. The first one was looking really from the physics and the dynamical system angle, where we reconstructed the attractor of the continuous PDEs of the system. We also looked at a very data science kind of Bayesian quantile regression, where we just took the data in and didn't really bring extra physical knowledge to it. And we also tried discretizing the system into different categories to simplify and understand how our forecasts perform better. So this is a fascinating system which offers very fertile ground for applying your favorite mathematical method. If you have ideas, do contact. And with that, I'll wrap up. Thank you.